All right, so this video is actually one of the first real interesting applications of integration that we encounter in this class. And the way that it works, or actually really what we're going to be covering, is the idea that we are going to use the integral to calculate the volume of some very specific shapes. And what I mean is we're going to have to put on our imagination caps for a second, and we're going to create... just draw an axis like we normally would. And I'm just going to put a stretched out version of our x squared graph here. So I'm going to put the graph y is equal to x squared right here. And the idea is that I'm going to say, let's say we just go to whatever this particular x value is. Let's say this is x is equal to 4. And I take that particular region, this particular shaded region right here, and I rotate it around the x-axis. My question that we're going to answer is, what would the volume be of the shape that we get when we do this? So, for instance, if I take that and we rotate it around, right, we're gonna get kind of like this bugle-esque sort of shape, right? And the graph will kind of mirror its image kind of down here, and we're gonna get kind of like this 3D sort of shape. Maybe I'll try and make it look a little more 3D, right? We're going to get this shape. And the question that we're going to answer is exactly what I said, right? If I shade this whole thing in, what is the volume of this shape? And one reason that we're trying to do this is we're going to build to some more advanced ideas in this class and in multivariable calculus, which is Calc 3 and Calc 4 for those of you at Pierce College. And the idea is that, the integral can be used in a variety of ways, and we're just trying to build, like some reasoning as to why, we might be using the integral to do this. So another reason that maybe kind of comes to mind is when it comes to AutoCAD and, creating 3D shapes, oftentimes you can take a cross-section of something, kind of like what we have here. We can take this cross-section, and if I know one cross-section of an object, then when I try and 3D print it, you really kind of just work with that one cross-section, and from it you can tell the computer, you can tell the program, exactly what shape you want it to print. Maybe you want to print a quarter of this, maybe you want the whole thing, etc. So how are we going to try and answer this question? We are going to do the following. Now, the first thing we're going to do is... we're going to pick a random x value just like we normally do. And I'm also going to draw a rectangle just like I normally do. Our same, infinitely small rectangle like so. But now, the last time I checked, when we were doing like total area, for instance, right? Total area, we would add up, right? We would add up a whole bunch of tiny areas. Right? That was the goal. Well, if we're going to be doing total volume this time, right? If that's the goal, total volume, then what do you think it is we're going to be adding up a bunch of? We're going to be adding up a bunch of tiny volumes. And that's pretty much a theme that we're going to try and stick to for this next little bit. But the one thing we don't have yet are tiny volumes. And so I'm going to just use exactly kind of what I said before, which is let's take this little cross section. Let's take this red cross section, and I'll try and highlight it in here real quick. Right, let's take that red cross section and let's rotate it around the x-axis. What kind of shape would we get? And so if I do this, and I'll try and do it graphically correct, right? Let's try and make it a little more accurate. If I do this, hopefully we see that the kind of shape that we get is a circle, right? If you take something of a fixed radius and you rotate it all the way around the x-axis, we're going to get a circle. So let's erase some of those and make some better cross sections for us. So let's kind of do. All right. So we're going to get like this round kind of circular-esque shape that's been generated by our straight up and down rectangle. So maybe I'll fill this in, this little rectangle right here. Okay. And the question is, if I were to ask you, what is the volume of this circle, right? What is this? That's kind of a place where we need to start. The volume of this circle. Well, Let's see. Volume itself is really just, the area of an object, or maybe what we might call the surface area of an object, multiplied by some thickness. Okay, now this is a unique way of approaching this idea, but it's one that I use a lot. Because, if you think about like the volume of a box, for instance, right? If I know the area of this bottom piece right here, like let's say this area is 20, then if I know the thickness, or what we might say is the height of this box, right? If I know that this is like 5, then I can quickly figure out the volume by doing the surface area of the bottom multiplied by the thickness of this object, which is 5, and you immediately get that the volume is 100. So we're going to take this idea and we're going to kind of run with it in the sense of, we're going to answer the question, well, what is the surface area of this circular shape? And last time I checked, maybe I'll put it up here, the area of a circle is just pi r squared. So that's not too bad. And then what's the thickness of this shape, right? What is the thickness of this particular kind of circular sort of shape that we've made, this disc, if you will? Well, the thickness is going to match the thickness of our tiny little rectangle that we drew, right? This tiny rectangle that I drew right here has a thickness of dx. So the idea here is that one of these tiny volumes matches this little formula, right? It's the area of the circle times its thickness, which is dx. And so if I wanted to kind of keep with this theme that total volume is equal to, adding up a whole bunch of tiny volumes, then what we're going to do is we're going to take this equation and we're just going to pop an integral in front of it. We're going to say, all right, it's going to go from whatever your starting x value is to whatever your ending x value is. What are we adding up? Tiny volumes, which is like, the surface area, right, times the thickness. Okay, times thickness. And we can just keep running with this formula, right? So from like A to B, we already know the surface area for the circle is pi r squared. The thickness is dx. And we're off to the races, right? We're almost done. The only thing we need to figure out is, right, I'm integrating with respect to x. I don't have an x here, I have an r, but thankfully, right, if I were to ask you what is the radius of this circle, right, if I were to draw it there, and I'll erase this one to kind of not confuse you all, but what is this radius? Well, the radius is just equal to the y value, right? It's the same concept from all of our other videos where we've been learning about how to do the area. The radius here is just going to be our pink y value, whatever it is on this particular function at that point. But in this case, our y value is equal to x squared. So for us, in this particular example, we would get the integral from whatever our starting x value is to our ending x value of pi times our radius, which is the function x squared, and then that thing squared because it's the radius squared, times dx. And this right here is how we could add up all of these little tiny volumes and get the total volume of this shape. Now, I understand my artistic abilities aren't, the best in the world, so I have a little screenshot here that kind of does the same thing. They use a slightly different function, but the idea is the same, where they take a particular x value and they draw a really, really skinny rectangle, and then they take that thing and they wrap it around. They're wrapping it around the x-axis like so, right? It creates this little tiny disc. And when you do it for every single x value kind of along this axis right here, right, and you start adding them all together, right, they really, really, really do a good job of giving you the total volume inside this particular 3D shape that we get when we rotate, just a single cross section. When I take a single cross section like so, right, a single cross section, provided like we're just going to here, and I rotate it around the x-axis, right, this is the shape I'm going to get. And it's comprised of, basically, we can think about it, of a bunch of circles or a bunch of little circles with a little bit of thickness, what we call discs. And that kind of is the reason why this section is, featuring what we call the disc method. So, for instance, let's do an actual example now. So, For example, what is the volume of the shape we get, rotating y equals the square root of x around the x-axis, in the region or between, we'll say x equals 0 and x is equal to 4. Okay, this is the question. And so the key thing for all of these, when you're doing any of your homework or anything like that, is to start off with a good sketch. And so usually this means that you have to be kind of well-versed in your functions if we're just drawing basic functions. So I'm going to sketch out y is equal to the square root of x, which looks something kind of like this, right? Y is equal to the square root of x. And then x goes from 0 to x is equal to 4. So I'll put that there. Maybe I'll make a dashed line, something like that. And so the region that we're going to be interested in is going to be, for us, this particular region here. Okay. And we're going to rotate it around the x-axis. And so we're going to be very careful and just kind of do your best to make accurate sketches. The more accurate your sketches, the easier it's going to be for you to do the harder versions of these questions, which we're going to get to a little later in this video. But for right now, again, so our goal is to find total volume. Okay. And total volume, that's what we get when we add up a whole bunch of tiny volumes. All right. And now, tiny volume, that's like surface area, right? Surface area times what I've said is thickness. Okay. And now the question is the surface area of what? Well, we first need to create a slice. We need to create a slice at some random x. So let's do that here. Let's create one of these little tiny rectangles, and let's rotate it around the x-axis. So we're going to get something that kind of looks like this. And we recognize, okay, this is just going to be the surface area of a circle again. And that equation is just pi r squared. That's not too bad, right? Specifically for us, we're talking about the surface area of the face of this little coin, if you will. We already know what the thickness is because of how we chose to draw our rectangle, right? Our thickness here is going to be dx, so we could fill that in right away if we so choose. And again, the radius is going to be whatever this distance is from the center of our circle out to the edge. So this is our radius, which in this case is just equal, so our r value, our radius is just equal to y. But because we have dx, we know that we can't leave this as just y. We need to convert it into x. And thankfully, we already have an equation that's ready to go for us right in terms of x. So our radius is the square root of x. And we can use that inside here to say, okay, well, last time I checked, if I take this radius and I square it, that's just going to leave us x. So we have an integral of pi times the square root of x squared dx. All we need left are some bounds, but that's not too bad. We can kind of see that, we're going to slide the x value left and right from 0 to 4. They do give us that in the problem, but there will be ones that we're going to have to figure it out on our own. And this is it. This is our setup, right? So if we do the integral from 0 to 4 of pi times x dx, we're going to get our answer. And you could pull this pi out because pi is just a coefficient, right? It's a scalar coefficient. It's just a number. So if you wanted to, you could write this as pi times the integral from 0 to 4 of x dx, and this shouldn't be too difficult for us to do. Okay, this seems to make enough sense. So let's see here. We did this example. Maybe we should do one that's a slight bit harder. Let's do one more example. Okay, so for example, let's do find the volume of the shape we get the shape we get rotating the intersection of y equals x and y equals x squared around, and I'll say in quadrant one, around the x-axis. Okay, find the volume that we're going to get. And so again, with all of these, every single one of these, you should start with a sketch. And you're going to have to be careful, right? You can use Desmos to guide you a little bit, but you really, really, really want to be able to do these on your own, especially for those of you going to multivariable calculus. This is just a back-of-the-hand requirement that you're going to need to have. But let's draw y equals x as this straight line like so, right? So that's y equals x. And now the graph of y equals x squared actually goes under this graph for a little bit anyways, and then it kind of pops up here. So this is y is equal to x squared. Okay, so again, what's our goal? Right, our goal is to find total volume. And total volume means we're going to add up a bunch of tiny volumes, right? And I'm keeping with this theme for a very specific reason, right? So we're doing surface area times our thickness. And again, you know, we're going to say, okay, well, we're doing these all by drawing straight up and down like slices. So let's say that for a particular x value, from whatever this x value is over here, I'll call it x2, and this x value here I'll call x1, right? We need to execute this integral for every single x value going kind of between those two. All right. And if you're curious, like what sort of 3D shape this is going to create, I can try and make a sketch of it. Let's see here. If I very carefully rotate this around the x-axis here, I might get this, and we should get like some reflection there. We're going to get some reflection here. And so we're going to get like some weird sort of 3D S shape that's kind of hollow on the inside, right? Because the actual shape, the part that actually contains a solid, is this part here, right? And it kind of reflects around like so. So whatever this 3D shape is, it's actually going to have a gap in this middle region here that's is kind of hollow. But the walls of it are going to kind of be like this thick sort of curved sort of shape. Okay, and so now, right, we're doing surface area, but we need to be a little bit more careful about what kind of shape we're going to get when we rotate this around the x-axis. And just for the sake of trying not to confuse you too much, I'm going to erase this lower part here just to make space for my drawing. Okay, and so again, when I said sketching is like one of the most important things, it really is, because you want to be super careful here as you sketch this shape. So you're going to notice now that when I rotate this piece around the x-axis, right, what is different, right? What's different about this one than the last one? So let's see if we can try and make this look somewhat realistic, right? The thing that's different is that there's a hole right in the middle of it. There's a hole right there. What it does is it's not creating a solid disc, it's creating a washer. Okay, and hence the second half of this video's title, right, is that we get a washer sort of shape. And so we have a problem now. It's a very small problem, but, you know, we have kind of like a big circle, and then inside of it we have a smaller circle, and there's stuff missing in the smaller area, right? We only really want to be getting this region here and not the inside one. But thankfully, you know, if we're trying to figure out, right, how do I come up with the surface area of this particular shape, it's not too bad, right? Because we still have some circles to be dealing with, so we're probably going to still be dealing with those area formulas pi r squared. But it's not too bad because the surface area here is just going to be, you know, the area of like the big circle minus the area of the small circle, right? It's not really too bad. If I calculate the area of the big one and then I punch out the area of the small one, that's going to leave me with the surface area of the shape that I'm actually interested in. And that's exactly what we're going to do here. So making space again, right? The surface area in this particular case is going to be the area of the big circle, or what's called in the textbook the outer circle, minus the area of the small circle, or what we might call the inner circle. Now, how about the thickness, right? What is the thickness of this particular washer, right? This washer, I can't even say it. This washer sort of shape. You try saying that 3 times fast. Well, the thickness of this washer is just going to be dx as it has been before. So dx again. And these area formulas are not too bad to work with because the big area is still pi r squared. Last time I checked, that's the area of a circle. But I'm going to put a subscript. I'm going to put like a b here for the big circle. Or in the textbook, you might see an o for the outer circle. And then we're going to subtract the area of what we get for the outer circle. Or no, for the inner one, for the smaller one. So what I put B for the bigger one, I'll put an S for the smaller one, okay? And so if we look at this, we just say, okay, well, we just have to be really careful with our drawing. We're almost done with it. All we need now is to come up with the radius of this outer circle, right? So what is the radius? And again, we're measuring from all the way from the edge here all the way down to the center of the circle. And last time I checked, that's just going to be the y value of this outer circle. But because we're integrating with respect to x, we're going to punch that in. And since this graph is pretty easy, it's just y is equal to x. So the radius of our outside circle here is just equal to x. And now let's do the radius of the smaller circle, or the inside circle. And so looking at our graph again, now we're talking about this distance just right here at the bottom, and I hope you can kind of see it. It's just this really tiny distance right there that I'm trying to draw, and that's just going to be the y value from this graph down to the x-axis. So again, this radius over here is also equal to the y value of the parabola, but in this case, that y value is given by x squared because we're integrating with respect to x. So we're almost done. We have the radius, we have the thickness. The only thing that's missing are the bounds, right? We said if I were to set up this integral right now, we would have an integral from the first x value to the second x value of pi times our x squared, and then minus pi times x squared, right? Where this is the x value here, and this x squared is coming from our other radius right there, and then we slap on a dx right at the end. You could put this in big parentheses if you want it to be the most technically correct. Yeah, and this is going to do it. This is going to get us the volume of this shape. And again, you could also notice that both of these terms have a pi in it. So if you were really feeling adventurous, you could factor a pi out from both of those and pop it on the outside here, because if you were to, pop it back in, it would distribute into both terms evenly. So this is totally fine as well. But our last thing that we really need to do, as I mentioned before, is we need to come up with these bounds. We need to actually figure out what are our x1 and our x2. But those aren't too bad because, again, we're looking at the intersection points on our graph. We're looking at those intersection points and figuring out what are the x values there, what are the y values there, and that's going to do it for us. How do you figure out intersections? Maybe I'll erase some of this since we've used it already. Right? How do we come up with intersections? We just set the graphs equal to each other. So I'm going to ask you, when does x equal x squared? Right? We're getting from those right there. And there's tons of ways to do this. The simplest is probably what you learned in Algebra 2, which is x squared minus x. from here, you can use the Pythagorean, or not the Pythagorean, you can use the quadratic formula if you want, but I would just say just both of these have an x. We can pull it out like so. And last time I checked, this is going to mean that either x is equal to 0 or x minus 1 is equal to 0, and that gives me that x has to equal 0 or x has to equal 1. And so that means that this coordinate up here has an x value of 1, and this coordinate over here has an x value of 0. And so that means that our bounds are going to go from 0 to 1 like so, and then we'd be done. Life is good, hunky-dory. This is going to do it for us. So I'm not going to go and multiply these things out and do the integrals just simply because that's not the intention of this video. The intention of this video is to really understand the intuition of what the heck's going on and how to set up these sorts of problems. So the last example that I'm going to do for this particular video, let's see, is I'm going to take the same one. I'm going to take the same thing that we have here, but I'm going to ask a slightly different question. So let's take all of this, right? And I just asked, about finding the area of the shape wrapping around the x-axis. But the next question might be, what if I ask you for the area wrapping around the y-axis? So another example, find the area, or find the volume we get wrapping the intersection of y is equal to x and y is equal to x squared around the y-axis, right? And I'm going to say in quadrant 1 again, right? That's what we want. So find the volume we get wrapping the intersection of y equals x and y equals x squared around the y-axis. And I'm just going to hit us with another drawing because that is the most important part, is to get this drawing done well. Y equals x, again, is just like so. Y is equal to x. And y is equal to x squared looks, part of it anyways, looks something like this. Y is equal to x squared. And so we're going to take this region, and I'm going to shade it in and do this properly this time. That way we can have really, really good visuals. But now we're going to wrap it around the y-axis. So a little curveball, we're wrapping it this direction. Well, if we're going to be wrapping it around that direction, there's actually, it turns out, 2 ways to do this, but I'm going to stick with one, and you can go to the next video to see the second method. But if we're going to go around the y-axis, if I were to take straight up and down strips like so and wrap it this way, you'll notice I don't have circles anymore, right? What shape do I have? Well, now I have cylinders, and that, again, this is the second version of doing this problem, which if you want to stop this video and jump ahead, you can go ahead and start the next video, which covers how to do it with cylinders. But I'm going to say, let's just, for this particular example, take horizontal strips, right? Let's take horizontal strips like this, and let's wrap that around the y-axis. So let's take that and create this sort of shape. Again, another washer, because this is really the method that we really want to be practicing right now. And I'll try and make it look as 3D-esque as I can. Okay. And again, what are we going to need, right? We're going to be adding up all these tiny volumes, right? Adding up all these tiny volumes. We're going to need some bounds. We're going to need some surface areas, whole bunch of stuff. So now, since we're talking about taking a horizontal strip at a random y value, that means we're going to be integrating in the direction of y. We're going to be sliding this thing up and down and taking a whole bunch of these little tiny rectangles that are going to get bigger and smaller depending on which y value we're at. And we're going to stop at whatever this top y value is, and we're going to stop down here at whatever this bottom y value is. Now, from the work we did in the last example, we know that the x value here is 1, which immediately, plugging into either graph, is going to give us that the y value here is also 1. And in the last example, we also saw that this x value was 0, which immediately gives us that y is equal to 0, again, in either one of those. And we know it's going to be the same no matter which graph we use because it's a point of intersection. So already we have our y bounds being y is 0 to y is 1. Turns out it just so happens to turn out that they're the exact same values as we got for the x bounds. And again, so now, we're asking ourselves, well, what is the surface area of this shape that we're looking at here? And this, again, it doesn't necessarily look like it based on my sketch, but I promise that's a big circle and a small circle, right? I'll kind of draw them over here. It's a big circle that has a small circle punched out of the center of it, like so. And so we're going to just say, all right, well, it's the outer area, pi r squared. I'll use the different subscript now, the outer one, minus pi r squared for the inner circle. And then what is, so this part here, this is the area of our shape. What's missing is the thickness. But now because we're drawing our strips horizontally, our thickness is now not dx, it is an infinitely small change in y, which we represent with dy. Okay, so we're pretty much 98% of the way there. All that's left to do is to figure out what these different radii are and get them in terms of y. So let's start with the outer radius. And again, we're just going to kind of go to our sketch and ask ourselves, what is the distance, right, from here, the center of this circle, all the way out to the edge of this rectangle that we've drawn, right? Because it's going to trace out this big circle. That's going to be our radius there. And so you say, okay, well, this big distance that I've drawn here, right, is basically the same thing. And I'm just going to erase this so I don't have too much written on here. It's the same thing as this distance right here, which is whatever this particular x value happens to be, right? So our outer radius is going to be this length here, which is the same thing as this distance, which is just whatever that x value is. But this particular x value is associated with which color graph, right? So when we're saying that this outer radius here, right, our radius here is equal to the x value, it's going to be the x value associated with the pink graph. Okay, it is on this parabola right here, and so that is going to be the x value that we're talking about. And so, okay, so we can pause there for a second if you'd like, and let's go on to the next one. So we're going to say, okay, well, I need the inner radius now, so let's write that down. And so we say, okay, well, I need my inner radius. Well, the inner radius is going to be, ooh, I erased too much. Let's use this one. All right, so the inner radius is going to be the distance from the center, but to the inner edge of this rectangle. So now on our x-axis, it's not all the way out there. It's only going to be this small distance here, and it's going to be wherever we end up at that particular x value right here, right? There's the bottom part of our rectangle there. And so to ask the same question, we might say, all right, well, what is this? What is that distance, right? How far is this? Well, it's the x value that is associated with now the green graph. So this is the x value at the green graph, right? The distance from the origin out to there is just x. That's not so bad. And now let's fill them out. So I'm integrating with respect to y. Thankfully, the green graph has a really nice transition between y and x. We happen to know that this x is just equal to y. So that's just fine and dandy. Now the pink one's more interesting because the relationship that we have for the pink parabola is y is equal to x squared. And I don't have x squared here. I just have x. And so we're going to need to write this as plus or minus the square root of y is equal to x. And then again, use what we know from working with graphs to recognize that this side of the graph is represented by the plus square root of y portion of this. The left half, for those of you who are interested, is the negative square root of y portion. And so we're just going to use that knowledge to say that the x value that we have here is the same thing as the square root of y. And that's it. So if we put it all together, we're going to get, let's see, I could factor out this pi, and the more you do this, you're welcome to pull the pi out immediately if you'd like, but I'm going to write the pi in the front. My integral goes from y is equal to 0 to y is equal to 1. Y is equal to 1, right? And that's represented here by the fact that I have to slide my y value up and down. And then we're going to have my outer radius squared, which is going to be my square root of y quantity squared, minus my inner radius squared, which was given by just y in this case, so y squared, and then the dy at the end, and voila, we have a fairly easy equation to work with here to get the volume of whatever this particular shape would be. So this is where we're going to pause this video for now. We're going to have to make a couple more videos to talk about some different obscurity, such as what if we're not rotating just around, the x-axis? What if we're not just rotating around the y-axis? What if, maybe using this washer method or the disk method doesn't work, right? I alluded to earlier that another shape we might get is a cylinder. So we're going to talk about that in our next video. And yeah, so we're going to try and cover all these nuances and get all your questions answered. But hopefully this is a good start that depending on the direction that we're going to rotate our slice, right? Whenever we decide to create one of these rectangles and slide it around a particular axis, that is going to help us determine what our surface area is that we're looking at. And in this case, in all the cases in this video, we've just been dealing with either circles or circles that are missing like a centerpiece, kind of like a donut, if you will. And again, in the next video, we're going to cover some more cases. So hopefully this wasn't too bad, that is not super crazy, and that you're a little bit interested in it. Again, one of the cool applications of this is like designing things in 3D and looking at cross sections of 3D printed objects. So if that's up your alley, there's more to this that we can definitely talk about in the future. But that's going to do it. So get on to practicing, and I'll catch you all in the next one.